morning. Today we shall start design of doubly reinforced beam. Design of doubly reinforced beam, and we shall consider the flexure part 1, and we shall have followed one few examples that we shall consider it as part 2. Design of doubly reinforced beam. So, doubly reinforced, that means reinforcement in the tension side as well as in the compression side. Steel reinforcement in both the tension and compression zones are called doubly reinforced beams. If we have a section which we are familiar in last few days, we are providing reinforcement. We are providing reinforcement in the tension zone only. If we consider in a normal general case, the bottom portion as tension and the top portion we are providing, which is nothing but in the compression zone. We are providing steel in the tension zone as well as in the compression zone. What we can do, but where do we need it? Where do we need this reinforcement? Why we have to provide that? We need that reinforcement because your depth is not adequate. You could not provide the depth required if you have to design it as per singly reinforced section. In that case, because it is restricted, maybe due to architectural point of view or maybe some other reason, so we have to provide. Then what we can do, we provide compression zone, we provide steel in the compression zone, and we do the design, and that is called doubly reinforced beam. It may happen that, say, due to moving load, particularly in support, where you have that compression as well as tension, there is a change of sign in the bending moment. There also you have to provide the reinforcement in the tension zone as well as in the compression zone. So, what is the design philosophy for doubly reinforced section? The design philosophy of doubly reinforced section, we shall provide the reinforcement in both sides. Let us say this one ASC, area of steel in the compression side, and AST, area of steel in the tension side. We can make in two parts. We can say that we are having a portion, this beam can take it a singly reinforced one, that means moment of resistance, if we consider it as a singly reinforced section only in the tension side. Therefore, I can say this portion, that area of steel, let us say AST1, area of steel AST1 due to singly reinforced section, plus the remaining portion I can provide it, assuming that only the steel action AC, area of steel in the compression side, and AST2, area of steel in the tension side. So, area of steel in the tension side, we have two parts, AST equal to AST1 considering singly reinforced section. We are assuming, we are considering here, we are taking it here as a balanced section. Due to balanced section, whatever steel we require, that is AST1 plus AST2. Individually this portion also will be in equilibrium, as well as this one also will be in equilibrium. AC and AST2 should not be equal, it cannot be equal, because the strain in the top portion and strain in the bottom, or in other way the stresses are different in two sides. Stresses here and stresses in the bottom are different. That is why that area, the force, whatever force we shall get it, the force is equal, because that one is supposed to be in equilibrium, but not necessarily that AC and AST2 will not be equal, because stresses are different into different zone. I could further explain. We have, if we draw the strain diagram, the strain diagram, it says somewhere say neutral axis. If we consider say Fe 415, we are assuming the steel is Fe 415. So, 0.0035, that is in the compression zone, the strain, whereas here 0.0038, since we are considering Fe 415. We are providing the steel at this zone in the compression side. So, the strain is different, and since strain is different, I could further explain this one, that doubly reinforced section 0.0035 epsilon SU. I have told epsilon SU, which is nothing but I can say so 0.0035 for Fe 415. What we can do, our strain diagram, 0.0035 concrete always same, but the other side it is dependent on the your reinforcement, steel reinforcement you have used. And we shall use this stress block. The stress block you are using this one. What we can do now, we are using this curve. It is dependent on the strain. Up to 0.002, we shall come back up to 0.002 strain. Beyond that, we get constant stress in concrete, which comes as 0.45 FCK, which will come as 0.45 FCK. This portion less than 0.002 strain, we shall get that in a parabolic one, we can get the corresponding stress, because we have to find out the stress. The other important part, that is the major part in our case, because since 0.0038 for AP 415 and we are getting say 0.87 FY, 0.87 FY, why? Because we are using that partial safety factor for materials, that is divided by 1.15 for steel. So, we are getting 1 by 1.15, which is nothing but 0.87 Fy. We should always remember 0.87 Fy. And the corresponding strain, we shall get it from this curve. For the strain computed, we shall get the corresponding stress, and that we shall use it to calculate our force. Okay. Now, let us come back. Let us come back in few cases when we have to provide the reinforcement. Let us write down when the construction depth is restricted and the moment the beam has to carry is greater than the moment capacity of the beam in concrete failure. When the construction depth is restricted and the moment the beam has to carry is greater than the moment capacity of the beam in concrete failure. So, moment of resistance for a section provided, if we have this section, let us say capital D, due to some reason we cannot go beyond this D, 450 millimeter, 500 millimeter, like that, but moment computed applied, that is more than the moment of resistance of this section. In that case, we have to provide the compression, that your reinforcement. The other one we can take, let us say number 2, where the bending moment at the section can change in sign. We can say that a continuous beam possibly, and there is a moving load, the vehicle is moving over the bridge. If it is continuous, most of the cases our bridges are simply supported, but if the bridge is continuous, in that case, in the support, the bending moment can change its sign, and in that case, because in the top, say generally it is compression and bottom tension, but due to change in sign, so it can happen the other way, the bottom compression, top tension. So we can get that we have to provide that adequate reinforcement, and in that case we have to provide that doubly reinforced, you have to use it as a doubly reinforced section. Well, let us come, there are different other points also. Now let us come that your analysis of doubly reinforced section. Analysis of doubly reinforced section. We shall come back for different other cases also, but before that let us take basic considerations. Number 1, RC sections in bending RC sections in bending fail when the compression strain in the concrete reaches the value 0.0035. We shall assume few cases. 0.005, that is the strain in concrete, and here also it is valid in doubly reinforced section also. Number 2, plane section remain plane even after bending. We can take one more consideration. Number 3, the stress at any point in steel and concrete can be taken as equal to the stress corresponding to the strain at that point of the stress strain curve I repeat, the stress at any point in steel and concrete can be taken as equal to the stress corresponding to the strain at that point of the stress strain curve for the material. So we shall get stress and strain at a particular section, that level, we shall get the strain. Strain is same for concrete and steel, that is same, but the corresponding stress we shall get it from the corresponding stress strain graph. From the concrete we shall get the parabolic and straight portion, and for steel the corresponding graph which is given in IS 456. From there we shall take the the stress. Well, now come to few procedures. What we have to do? We have a section and we have a neutral axis. The effective depth D, width B, stress strain curve, let us draw. Point 0035. What about this portion? Let us say this is effective depth D dash. D dash equal to clear cover plus phi by 2. Our interest here, this is epsilon s. Our interest here, we can divide it into two parts. One that I have already told, one that singly reinforced section plus you supplement with steel in the compression side and as well as in the tension side. We shall get the curve we have, let us say this is T, C, C due to concrete only, compressive force due to concrete only, and we have C, S. Therefore, C total force in concrete equals CC plus CS. CC we can get, say due to concrete failure, I can write down this way: CC equal to K times FCK BD square. Please check the previous class note. K 0.138 FCK BD square if it is Fe415, we can write down. And the CS, it is nothing but the stress in steel multiplied by the area of steel in that zone. And we have two lever arms. One lever arm, this is one, let us say ZC, and the other lever arm, let us say ZS. ZC and ZS. D is the effective depth.
That won't be between the two reinforcements.
No, D is never within between the two reinforcement. D is always from the top fiber. D is always from the top fiber, and that's why we have got another parameter say K2D. It means that from the top fiber, what is the position of this resultant force, compressive force, which is 0.42 D or 0.416 or 0.42 D that we are getting. So we can write down mu equal to Cc concrete times, I can write down here say Zc the lever arm plus Cs times, it is always D minus D dash, it is always D minus D dash. So I think I can write down, instead of that, let us write down here plus Cs D minus D dash. I mean to say Z dash equal to D minus D dash. Okay. And this Cc is nothing but K FCK BD square, depending on the steel used. Depending on the steel used, we shall get. We have to find out the strain. The section we are providing here .0035, we have to find out epsilon SC in the strain in the compression side at the steel level, where we are providing the steel, that is at a distance D dash from the top fiber, D dash from the top, and we have X. What about epsilon SC? Epsilon SC will be equal to 0.0035 1 minus D dash by X. Epsilon SC 0.0035 1 minus D dash by X. If we assume if X maximum could be say D by 2, so we can write down D dash by 0.5 D. If we can have, let us draw the stress strain curve, or I think I can show it here. Our objective here, the strain where we are providing the steel reinforcement, the D dash, if it is more than 0.002, the strain greater than 0.002, what we can get? We can always get 0.45 FCK. We can get 0.45 FCK. We are assuming if X max equal to D by 2, 0.48 D, XU by D, XU by D for FE 415, that we get 0.48. Okay. We can get it in IS 456, we can also derive it also. XU by D equal to 0.48. That means it is coming say reasonable assumption that 0.5, XU equal to 0.5 D maximum. So we can write down this expression where it comes as D dash by 0.5 D equal to say 0.0015 by 0.0035. Therefore, I can write down d dash by d equal to 0.214, approximately say 0.2. We can say d dash by d, if it is 0.2 or less than that, we shall get the stress in concrete 0.45 FCK. We shall get stress, that is 0.45 FCK. The other portion, because we are getting the strain, at that level, so corresponding stress we shall get it from this curve. So the corresponding stress we shall get it from this curve. Instead of that, let us tabulate it. Let us find out in this curve that for the strain how much stress we shall get. For a particular strain, how much stress we shall get it from this curve. So stress level in terms of yield, we shall start with 0.8 into 0.87 FY, 0.85 into 0.87 FY, 0.9, 0.95, 0.975. We shall linearly interpolate, because if we get the corresponding strain, so we can linearly interpolate. We shall take these few points in our case. Let us take Fe415 strain and stress. We shall get at this stress level 0.8 into 0.87 FY, 0.00144, the strain, corresponding stress 288. Let us give the unit. 0.00163, 306. At 0.9, 0.00192, 324. 0.00241, 342. 0.00276, 351. 0.0038, 361. And we are getting from this curve. You can directly get it using scale, directly also you can get the corresponding stress, but instead of that it is customary that we can tabulate it, and from there we can just linearly we can interpolate. If the corresponding strain comes within this limit, so we can linearly interpolate and we can find out the corresponding stress. So it is better to use this type of table. What about Fe4 500? The strain, let us give a margin, strain and the stress, we get 0.00174, 347, 0.00195, 369, 0.00226, 391, 0.00277, 413, 0.00312, 423, 0.00417, 434. We have for Fe415 and also for Fe500. We can get the strain and corresponding stress, and we shall linearly interpolate to get the corresponding stress at a particular strain level. We shall come to the next level, say analysis of beam. One, let us elaborate the whole procedure. Calculate mu for concrete failure. As a singly reinforced beam. We can write down this part as mu1 equal to 0.149 FCK BD square for Fe250 equal to 0.138 FCK BD square for Fe415 equal to 0.133 FCK BD square for Fe500. We shall use the appropriate formula to get the moment of resistance for singly reinforced section when the section is assumed to be failed due to concrete failure. mu1 for Fe250, for Fe415, for 500. Step 2, determine the balance steel required. We shall use the formula that 0.87 FYAST, the steel also has reached the maximum stress, equal to 0.36 FCK B times XU. We can write down it as AST by BD equals 0.36 by 0.87 just rearranging, times FCK by Fy times XU by D. Let us repeat, FE 250, FE 415, FE 500, XU by D 0.53, 0.48, 0.46, PT. What is PT? In other way, AST. AST equal to PT times BD by 100. So PT equal to 21.97 FCK by Fy equal to 19.82 FCK by Fy equal to 18.87 FCK by Fy. If we calculate, we shall get this. Either you can remember this one, or we can start from the very first principle. You can calculate. Our objective here to find out, because it is easier to remember, which is nothing but the steel force equal to compressive force. From there you are getting that value, and we can find out AST equal to PT BD by 100. Therefore, we can write down PT. What I feel, most of the cases at the time of design, when you are doing in design office or at your home, your books, other things are available. But when you are doing in the exam, so you should at least follow certain procedure so that you can do it without consulting any book. So that's why it is better to start from the first principle, though it will take time. But if you do practice, if you solve so many problems, then you will find out automatically you can remember these values also. Number 3, determine stress in compression CS equal to FSC. FSC is the steel that in the concrete, in the compression side, FSC minus FCC times ASC. What we mean, when you are taking this section, there are reinforcement. When you are considering the singly reinforced section, already we have taken this area. However small it is, the compressive, say your concrete stress, but already we have taken this area. That's why we are deducting that ASC. When you are taking the steel, so we are taking FSC minus FCC times ASC. However, we can neglect this FCC because it is very, very small. So, because you are taking say 20 Newton, 20 times say 0.45. So, that means 9. If we find out 0.45 FCK, if we take 20 Newton per square meter M20 grade of concrete, we are getting 0.45 times 20, which comes as 9. Whereas 0.87 FOI, say for Fe415, which comes as say almost say 361. So, in other case we can neglect this 9, and our code also, that in annex G you will find out that it neglects, and we can write down CS equal to nothing but FSC times ASC. Okay. So, this is your that compressive force due to that steel in the compression side. Number 4, we have two parts of moment of resistance. One is mu1, another one mu2. Find mu2, we can say additional moment, let us say in compression failure. Due to compression steel. mu2 equal to, let me draw the figure. This length is d minus d dash. ASC. So, mu2 equal to FSC, which you have got it from the strain, times ASC the force, times the lever arm, which is always d minus d dash. mu2 FSC ASC d minus d dash. Let us write down ASC, area of compression steel, and FSC, stress in compression steel, corresponding to its strain. So, we have two parts, mu1 and other part is mu2. Number 5, find total mu for concrete failure. We can say, you can designate it as MUC equal to MU1 plus FSC ASC times D minus D dash. Number 6, find AST2 by tension failure. We are analyzing the beam that where AST is given. So, I can write down as AST2 will be equal to AST minus AST1. AST1, because we are having two parts, area of steel AST is the total tension reinforcement in the tension side. Due to singly reinforced section, the corresponding balanced steel we shall get it, that is say AST1, and remaining portion AST minus AST1, which is AST2, that we shall get it to provide that your in equilibrium position for the compression reinforcement, and that one we call it as a steel beam theory. So, we are having two parts, that means we are providing as if that we are providing steel at the top, we are providing steel at the bottom, and then we are increasing the moment of resistance of the beam. Number 7, find total mu for tension failure considering final failure to be due to tensile steel reaching yield. We are taking this case, we have already done in the concrete side, concrete failure. Now we are talking the other side, the tension failure. Here we are assuming that we shall reach the yield stress of steel, that is 0.87 Fy. Then what we can write down? MUT, we have already done MUC, so MUT will be equal to MU1 plus AST2. AST2 is the remaining portion times 0.87 Fy d minus d dash. This MU1 plus AST2 times 0.87 Fy d minus d dash. We are taking the same principle. AST equal to AST1 plus AST2 and the dividends are different, so d minus d dash. So we know MUC and we know MUT. Out of them, which one is the minimum one? That one will be your moment of resistance of that doubly reinforced section, and this is called analysis of doubly reinforced section. The section where all the detailing is given, that your depth, width, reinforcement at the top, that means the compression side in general case, reinforcement at the bottom, I mean to say in the tension side, tension zone, concrete grade, steel grade, and we have to find out the moment of resistance. So if we summarize, we shall get, we are making it in two parts. First part as if that we do not have the compressive reinforcement. So if we take out the compressive reinforcement, we can consider it as a balanced section. So what is the moment of resistance due to concrete failure, that we can find out, which is nothing but mu equal to capital K FCK BD square, K in a particular case for Fe415, that is 0.138. So mu equal to 0.138 FCK BD square, that just can remember. The corresponding area of steel AST1 we can get it from the balanced section, because steel also simultaneously reaching the yield stress. So AST1 we can find out. The total area of steel AST is provided minus AST1, that one we are getting, that it will be in consideration with say doubly reinforced section. So ASC at the top in the compression side and corresponding AST2, the balance of AST minus AST1, from there we shall find out the corresponding moment of resistance. So we are doing in one side, we are doing it due to concrete failure, the other side we are doing it due to steel when it is reaching the yield stress. We shall find out the two moment of resistance, and we shall, which one is the lowest, obviously we have to take that. So mu moment of resistance equal to minimum of, say I can say AMUC and AMUT. This is called analysis. We shall continue with that design of doubly reinforced beam. When moment that mu is given, that applied moment is given, and width of the beam given, depth also given, say we have to find out the reinforcement other thing, that is called design. Okay. So, let us stop in this one. So, we shall continue again in the next class today itself.